Let's talk about something that breaks every rule of physics you learned in school. It's not a solid, not a liquid, and not a gas. It's somehow all of them, and none of them, at the very same time. First, picture a perfect crystal. Its atoms locked into a rigid, perfectly ordered grid. Then, imagine that same crystal flowing like a frictionless liquid ghost that could slip through the tiniest cracks without any resistance. It sounds like pure science fiction, a material that is simultaneously frozen in place and flowing freely. For decades, this was just a paradox on a blackboard, a ghost in the quantum machine. But it's not science fiction anymore. In a wild experiment that stretches the limits of reality, scientists have finally created this impossible material, and they forged it by trapping the most ethereal thing in the universe, light. They took particles of light, which have no mass and no substance, and coaxed them into a bizarre partnership with matter, forcing this hybrid to become a crystal that flows without friction. The question is no longer if a supersolid can exist, but what we can do now that we've captured light itself in this impossible state. This isn't just another discovery, it's a door to a new reality, one that could unlock technologies we've only dreamed of. The quantum ghost. What exactly is a... To really get how big of a deal this is, we need to wrap our heads around the paradox at its heart. How can something be a solid and a superfluid at the same time? A solid, easy enough. A diamond, a block of ice, a grain of salt. On a microscopic level, these things are all about order. Their atoms are locked into a highly structured. For decades, this question was one of the biggest unanswered challenges in physics. Hints of it were seen in experiments, but the evidence was always fleeting and fiercely debated. Creating the insane conditions needed to even try to see this state was one of the hardest jobs in science. Until now, repeating pattern called a crystal lattice. Think of it as a disciplined army of soldiers, standing in perfect rows, each one in its assigned spot. This structure is what gives a solid its shape and hardness. The particles wiggle a bit, but they don't flow. They're fixed. Let's look at these two states of being that really shouldn't get along. First, it has zero viscosity. Absolutely no internal friction. Physicists have wondered, could you have both? A material with the perfect, repeating structure of a solid crystal, but which could also flow through itself with zero friction, like a super. This hypothetical state was named the super. It would be like our army of soldiers, standing in their perfect ranks, but at the same time, soldiers from the back could flow effortlessly through the front ranks without a single collision. It's a state of being that is both frozen in a pattern and in perpetual, frictionless motion. It's the Schrödinger's cat of matter, solid and fluid at the exact same time. It can flow forever without losing energy. It can literally climb the walls of its container and crawl out, defying gravity. It can seep through molecule-sized cracks that would stop any normal liquid cold. It's a frictionless fluid, a liquid ghost. Now, let's get weird and dive into the quantum world to understand a super. This is where your everyday intuition just completely falls apart. A superfluid is a quantum state of matter, famously seen in helium when it has cooled to just a few degrees above absolute zero temperature possible. Down there, quantum effects take over. The individual helium atoms lose their identity and start acting as one single, collective wave. The wildest property of a superfluid, for over 50 years, it's a concept that just seems wrong. How can particles be locked into a grid while also flowing freely as if that grid wasn't even there? Forging light. How did they actually do it? The old school way of trying to make a supersolid was a nightmare. It involved cooling a gas of atoms to temperatures colder than deep space, just fractions of a degree above absolute zero. While a few teams finally managed to do this with atoms back in 2017, the results were incredibly fragile and almost impossible to study. So, a team of researchers decided to try something completely different. Instead of wrestling with supercooled atoms, they asked a crazy question. Could they make light bend to their will and form a supersolid instead? Not a glass jar, but a ridiculously sophisticated photonic device. They started with a piece of gallium arsenide, a material used in high-end electronics, but they didn't leave it flat. They used incredible precision to etch a series of microscopic ridges onto its surface. Think of it like a tiny, corrugated landscape, a set of microscopic hills and valleys perfectly shaped to interact with particles of light. This ridged structure was meant to act as the crystal lattice, solid part of the equation. To pull this off, they built what they called a quantum theater, tiny stage designed to make light do things it was never meant to do. The easiest way to picture it is as a particle of light wearing a coat made of matter. Photons on their own barely interact with each other. They just pass right through one another. The carefully designed ridges on the surface acted like a quantum egg carton, trapping the polaritons. This forced the flowing fluid of polaritons to arrange itself into a fixed, periodic pattern, matching the ridges. They had become ordered. They had formed a crystal. That was the solid part. But by giving them this matter-like coat, the polaritons could suddenly bump into each other, influence each other, and behave like a fluid. The entire collective of trapped polaritons could still move across the lattice as a single, coherent quantum wave, with zero internal friction. It was a perfect superfluid. They had created a photonic First, they needed a trap for the light. The intense light excited the material, causing the photons to interact and fuse with the electrons inside the semiconductor. This powerful interaction created brand new, hybrid particles called polaritons. Next, they needed the substance. That came from a laser, which fired a beam of photons or particles of light at this custom-made stage. And here's where the quantum magic starts. When the laser hit the gallium arsenide, the photons didn't just bounce off. A polariton is a strange beast that is part light and part. The researchers then pumped more and more laser light into the system, creating a dense fluid of these polaritons. But at the same time, because these particles were still part light and fundamentally quantum, they never lost their ability to flow. They had done it. They had a rigid, crystal-like structure and a frictionless, superfluid flow, all in a system made not of atoms, but of light-matter hybrids. Beyond the experiment. Why does this breakthrough matter? Okay, so creating a new state of matter is cool enough to be written into physics textbooks forever. But the ripples from this discovery go way beyond just scientific curiosity. This isn't just some lab curiosity. It's a key that could unlock some revolutionary tech. Atomic supersolids are like trying to study a rare fish that only lives at the bottom of the Mariana Trench. The setup is insanely complex and the conditions are extreme. We're in the middle of a second quantum revolution, and strange materials like this are exactly what we need to push it forward. These new photonic they don't need those extreme cryogenic temperatures, and can be built right onto semiconductor chips. Researchers can now poke and prod at a supersolid just by tweaking a laser or changing the design of the chip. It's an unprecedented quantum playground for figuring out the fundamental rules of the universe. This could be used to create high-precision sensors of incredible accuracy, able to detect tiny changes in gravity, magnetic fields, or temperature, for everything from medical imaging to deep space astronomy. First of all, making a supersolid from light-matter hybrids gives scientists a much easier way to study this bizarre quantum phase. By learning to control light in such a profound way, forcing it into a structured, solid-like state, we open the door to totally new kinds of optical devices. You can imagine optical circuits with near-perfect efficiency, new ways to store information in light, or even new methods for storing energy. This isn't just about understanding light better. It's about making light do things we never thought it could. But the real game changer is what we could build with this. Think about quantum computing. Quantum computers promise to solve problems that are flat out impossible for our best supercomputers. But their building blocks, called qubits, are incredibly fragile. The slightest vibration or temperature change can make them lose their precious quantum information. A problem called decoherent. A superconductor is a material that conducts electricity with zero resistance, meaning no energy is lost. The frictionless flow in a superfluid is basically the uncharged cousin of superconductivity. By studying how flow works without friction in these new, more accessible supersolids, scientists can get fresh clues into the physics of zero resistance. While this won't give us a room temperature superconductor tomorrow, it's a powerful new tool for tackling one of the greatest challenges in science. It's the biggest headache in quantum computing. A supersolid could be a solution. Its unique nature is stable. Rigid structure combined with a perfectly synchronized quantum flow might be the perfect recipe for a new kind of ultra-stable qubit, one that's naturally shielded from outside noise. Then there's the holy grail of superconductivity. The supersolid's properties also open up more direct uses. Its collective quantum state is exquisitely sensitive to everything around it. And finally, this is a huge step for photonics, the science of using light for technology. We already use light in fiber optic cables. The unwritten chapter. This experiment isn't the end of the story. It's the beginning of a whole new field. Physicists around the world are already jumping on this, and a ton of new questions are now on the table. The first step is to get to know this new state of matter, inside and out. How stable is it? How does it react when you poke it? What happens when you melt it or freeze it? Understanding these transitions is key for both fundamental science and forever hoping to build anything with it. Being able to engineer these quantum states on demand is how you get from a cool lab demo to a useful piece of tech. Another big question is about scaling it up. Can they make bigger Can they design different crystal structures by changing the chip's landscape? Scientists will also start mixing and matching. How do these photonic supersolids interact with other quantum materials? Could you put them on a chip with other quantum parts to create hybrid systems? Maybe a supersolid could act as a bridge to pass quantum information between different kinds of qubits. The ultimate goal, of course, is to actually use the weird and wonderful properties of this material. The road from a lab discovery to a device in your hand is always long, but that journey has officially started. Researchers will now start designing proofs of concept, a more stable qubit, a more sensitive sensor, a better optical switch. We are watching the birth of a new branch of physics. The seed has been planted. Now the hard work begins to see what kind of fruit it will bear. We are at the dawn of the age of supersolid light, where the line between pure energy and solid matter has been beautifully and permanently blurred. So, at the end of the day, what this shows us is that the universe is far stranger, more flexible, and more interesting than we give it credit for. Scientists in Italy have peered into the quantum realm and bent the rules, taking light and matter and convincing them to become both a perfect crystal and a frictionless fluid. This discovery reshapes our very definition of matter and gives us a new toolbox to build the future of quantum technology. From reality-bending computers to hypersensitive sensors, the potential applications are just as mind-bending as the science. It's a powerful reminder that, even now, there are still profound secrets about the nature of our universe just waiting to be found. If you want to stay on the cutting edge of physics and explore more discoveries that are shaping our future, make sure to subscribe. We'd love to hear your thoughts in the comments. What potential use for a light-based supersolid gets you the most excited?